Hello, welcome you all. In this video, we will look into the energy balance under unsteady state condition for preheating culture medium. So here you have a culture medium which you have to preheat it to a required temperature. Remember, when you have to heat it, there are some essential item, not only the liquid, along with that the vessel also you may have to heat it, two component system. So let's have a look into the concept of using a numerical. Let's do it. Here is the numerical. You may pause the video, have a look at the numerical, then let's go ahead with the explanation. Okay, let me explain the problem for you. In this problem, we have a glass fermenter and this is used for culturing of hybridoma cells. So it has got nutrient medium. The current temperature is 15 degrees Celsius of the liquid. In fact, that's along with the fermenter also. The fermenter also has the same temperature. The fermenter is wrapped in an electrical heating mantle which delivers heat at a rate of 450 watt. So this fermenter is surrounded with the heating mantle. Heating mantle is present, electrical heating mantle. It delivers some energy, it's 450 watt. In fact, that heats up the fermenter as well as the liquid inside the fermenter. Before inoculum, the inoculation is added, the medium and vessel must be at 36 degrees Celsius. So this is your requirement. You have to heat to 36 degrees Celsius from 15 degrees Celsius. The medium is well mixed during the heating. So there is a stirrer, agitator inside that mixes the medium neatly. So uniform mixing is there. So you can assume that the temperature inside the liquid is uniform at a particular temperature. Use the following information to determine the time required for medium preheating. So we're heating the temperature liquid from temperature of 15 degrees Celsius to 36 degrees Celsius. It means the temperature is varying with respect to time. It's an unsteady state condition. So you are expected to find out how much time is required to heat in this particular case. For this we require some information. What we have, mass of the glass vessel, that is the fermenter vessel, and nutrient medium. Both mass is available, their specific heat is available. Look at that, it is in calorie per gram Celsius. We may have to modify it because it is in kg here, it's in gram here, it's in calorie, and here we have watt which is in joule per second. So all this modification, let's go ahead and do it. Now the basis what we'll take is the mass of the two things. We'll take it as the basis, glass fermenter and the nutrient medium masses. We'll take it as the basis to do all the calculation. So let us assume that medium is well mixed during the heating, so the temperature remains constant inside. There is no heat loss. This is very important. We'll assume that heat is not lost to the surrounding and all the heat given by the electrical coil is added to the fermenter to increase its temperature as well as the liquid temperature, right? Let us consider the reference temperature as 0 degree Celsius or 273 Kelvin for our analysis purpose. Mass of the fermenter and mass of the medium, we'll note it down. We'll give a notation here. V for vessel, this is M for the medium. Okay, this is notation M, this is notation V, capital M for the mass. And specific heat of the vessel and the medium, let us write it and let us convert that unit. So calorie to joule, you have to multiply by 4.186, gram in the denominator, so you may have to multiply with the 1000, right? So you end up with 837.2 joule and possibly 3851.1 joule per kg Kelvin. Alright, this is the schematic representation. You have the heating coil outside, right? You have the mantle outside. From that the heat is added and you have a stirrer, the liquid is inside. This is how it looks like. So you have the complete insulation and no heat is lost. So the rate of heat supplied, let me take it as Q, the notation, it is 450 joule per second. The temperature of the vessel in the medium, this temperature over here, before T is equal to 0, it is 288 Kelvin, right? So that's 15 degrees Celsius. So after T is equal to 0, it starts increasing, and that's T, variable T, which increases with respect to time. We use a word called as transient, we use a word called as dynamic, we also use a word called as unsteady state. All mean the same. Transient, dynamic or unsteady state, energy balance means the same thing. So considering transient energy balance or unsteady state energy balance equation, let us not do any mass balance here because nothing we are adding, it remains as it is. over the time. So we will not do the mass balance in this case here. So rate of heat supplied to the system will be equal to rate of accumulation of enthalpy to the system. So there is no inflow or outflow, right? So there is no inflow or outflow in this case. So that is why you have you don't have what you call it as the energy that is coming in, the enthalpy that is coming in. So rate of heat supplied to the system by whom the heating coil will be equal to accumulation of enthalpy. Accumulation of enthalpy means is temperature increased because of accumulation, right? So rate of heat supplied to the system will be equal to Q, and rate of accumulation, as I mentioned to you, it is starting with a d by dt, right? So Q is watt per second, sorry, joule per second, that's in watt. Whereas here rate of accumulation per second we already have it, so we need a term d by dt, some accumulation that's happening for the energy part, that's enthalpy part. Now enthalpy, how do we write? mcp delta t. But remember, the heat is being given to the vessel first, then it is being transferred to the liquid. So you need to consider vessel as well as the liquid in this case. So both the cases it is mcp delta t. But when we write mcp delta t, I'll write mcp delta t for the vessel first, mcp delta t for the medium next. Alright, so it is mv cpv T minus Tref, mm, cpm, T minus Tref. What's something common here? The temperature. Temperature of the medium, temperature of the vessel remain the same, whereas specific heats are different. Mass of the vessel and mass of the medium is different. So the unit of this one, mcp delta T, is joule. Joule per second. It gets uniform now, right? Fine. Let's go ahead with the solution of this. Q is equal to, since m and cp are constant, I can take it out. As you know already, we have done earlier, t minus t ref. In this, if I do the differentiation with respect to time, we'll write dt by dt. T ref is a constant, so differential of t ref with respect to t is a 0. So straight away this is written mcp dt by dt plus mcp of medium dt by dt. So in this common is dt by dt. I'll take it out. MCP for vessel and the medium, I can take it up as a common term. We'll have to integrate. When we integrate, let's look at the limit. At t is equal to 0, the temperature is 288. At t is equal to t, the temperature is t. So even though I know the final temperature required, let me keep it as a variable. Later we can substitute and find the solution of it. Right, here is the solution for this. So when you integrate, it's a simple integration, mcp delta t. It is t with the integral of integral limit of 288 to t, right? So t minus 288. So integration is simple. All these are constant. So constant into dt, you have constant. Integrating a constant is variable itself. You get it, variable power 1, that is t power 1. You get it, t. It's just like integral of k dx. You get k into x, right? Now you have to put the limit, substitute, simplify. So the q value, your important thing you need to observe here is ensure that all the terminology that you use is either in like temperature in Kelvin, mass in gram or kg, specific heat in joule per kg Kelvin, right? So time is in seconds, or so ensure that it's in a proper particular uniform unit. That's very important. Unit consistency is very important. Now when you simplify, the t will be equal to 1846 second. So the decimal accuracies are not important here because it's in seconds. This much is sufficient, 1846 seconds. And when you convert it to minute, that is divided by 60, right? 60 second is equal to 1 minute. So divided by 60, when you do it, you get 30.7 minute, or otherwise it's called as half an hour, right? Now here, how did I get this? I have converted, used this t for 36 degrees Celsius. That's what is our requirement, right? This is a generic equation. This is a generic equation with the t as the variable. Whereas when you substitute t, you get 1846 second. Remember, this is for the case of 36 degree. If you change the temperature, you will get a different value. Required temperature, how much time it takes, you can verify. Alright, that's it for this class. Thank you.